At GoPro, I lead a team that builds the eyes of GoPro's popular action cameras. And today I'm going to talk to you about building the eyes of a vision system. Let's begin by talking about light. What is light? Well, light can be represented as both a particle and an electromagnetic wave. And when discussing image sensors, we tend to rather casually switch between the two. A photon is a light particle, and the energy determines the wavelength. Higher energy means shorter wavelength. Energy equals Planck's constant multiplied by the speed of light divided by the wavelength. And when light is visible to human beings, we perceive different wavelengths as different colors. Intensity of light is equal to the number of photons. The human vision system is sensitive from about 380 nanometers up to 740 nanometers. Below 380, we have ultraviolet. Above 740, infrared. Let's explore the different bands of light in a little bit more detail. Visible, as mentioned, 380 to 740 nanometers. There, we can use CCDs and increasingly CMOS image sensors, CIS. Moving out beyond the human visual response from 0.74 micron to 1 micron, we can continue to use CCDs and, in particular, near-IR enhanced CIS. Between 1 micron and 2.5 microns, we have the shortwave IR band, and here we have to start using different sensor technology. Typically, for shortwave IR, we use in-gas sensors. From 3 microns to 5 microns, we're in the medium wave IR band with a number of sensor technologies, including indium antimonide, mercad telluride, and 3.5 semiconductor superlattices. And this is starting to move into the classic thermal imaging of heat. The next thermal band is 8 to 14 microns, long wave IR. Typical sensor technologies are micropolometers, and again, mercad telluride. You may notice there's a gap between 5 microns and 8 microns. That's because water vapor in the atmosphere absorbs light in that band. Image sensors make use of the photoelectric effect. Electromagnetic radiation hits a material and dislodges electrons. And those electrons can be collected and counted. An interesting aside is Albert Einstein was awarded his Nobel Prize for work on the photoelectric effect, not for his theory of relativity. Anyway, the number of electrons is dependent on both the intensity and wavelength. So quantum efficiency, QE, is the ratio of the number of photons collected to the number of photons incident. QE is sensor specific, even between different CMOS image sensors, and is frequently normalized and shown as relative QE to obscure intellectual property. The peak QE of silicon aligns rather nicely with the peak response of the human visual system at 555 nanometers. And on the plot on the right, the black line shows an idealized CMOS image sensor quantum efficiency overlaid on top of the sea-level solar spectrum. Now let's go into some details around CMOS image sensors. CMOS image sensors leverage complementary metal oxide semiconductor, CMOS, manufacturing processes. Each pixel contains a photodiode and a current amplifier. This is what's called an active pixel sensor. And a defining feature of CMOS image sensors is a very high level of integration. Each image sensor is really a system on a chip, typically with on-chip ADCs, timing control, voltage conversion, corrections for things like black level, defective pixels. So apart from some specialist sensors, like those from Foveon, capturing color from a single image sensor requires spatial subsampling. So we place a color filter over each photodetector, and the diagram on the upper right shows a cross-section for a couple of pixels. You have photodiodes, and build up on top of those. In this example, you have a red color filter material, a green color filter material, and this forms what's called the color filter array. On top of the CFA, we have micro lenses which help focus the light so we can collect more light in the photodiode. When producing color images for human consumption, almost always we use the Bayer color filter pattern that's shown in the center, which has two green pixels diagonally opposed, and then one red and one blue pixel. And that generates the kind of quantum efficiency you see in the plot in the lower right. You may notice that that goes out beyond the human visual response. And so if we want to have natural color, we have to put an IR cutoff filter that cuts beyond 740 nanometers. So having this spatially subsampled representation of color, we then have to use a demosaic algorithm, which interpolates the missing colors to generate a red, green, blue value for each location. In addition to the Bayer color filter pattern, there are a lot of novel color filter patterns that can be used for specialist applications, like clear, 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 red, which is quite common for automotive, red, green, blue plus IR, where the IR in this case is an infrared path filter. CMOS image sensors have certain characteristic noise sources, and when developing a system, some awareness of these is necessary. First is shot noise. So this is noise that's intrinsic to the quantum nature of photons. It's an uncertainty in measurement, and the shot noise is equal to the square root of the number of photons. Read noise is the RMS noise of the sensor circuitry, typically measured in electrons. And then we have a number of different sources of what's called fixed pattern noise. Pixel fixed pattern noise are pixel to pixel dark offsets. This can include dark signal non-uniformity, which changes with integration time, which is the same as exposure time, and temperature. Column fixed pattern noise, these are per column dark offsets. And this one can be tricky because it's visible well below the pixel temporal noise floor. So down to say 1/20th of the read noise. And that's because it's fixed in location and has structure. Row fixed pattern noise are per row dark offsets. Then we have photo response non-uniformity. So this is a pixel to pixel variation in responsivity or sensitivity, effectively a gain error. And then row noise. This is a particularly important one. So this is per row variation in the black level of each row. And it's dominated by temporal noise. I mentioned row FPN earlier. That's generally not an issue in modern CMOS image sensors. CMOS image sensors tend to have a number of hot pixels, certainly for any that are commercially available. This was true in CCDs, but the numbers are higher in CMOS. And these are pixels with high leakage. The plot on the upper right shows something that looks a bit like a Poisson distribution of pixel counts versus pixel value. You can see there's a couple of bumps out beyond the tau, which are typically caused by defects, things like metal contamination into the photodiode. And so these are seen for long exposure captures and or high temperatures. And these need correcting or really hiding by the image processing pipeline. And to do that, we can generate a static map that's programmed at the factory. We can use dynamic detection and correction, or a combination of static and dynamic. And then we can place the hot pixels with the average of neighboring pixel values. If it's a color sensor, that should be from the same color plane. We have two types of shutter control on CMOS image sensors, global shutter and rolling shutter. In global shutter, all sensor rows capture light at the same time. In rolling shutter, we reset one row at a time and then read each row out n row periods later. And the integration time, exposure time, is the row period multiplied by n. This creates some rolling shutter artifacts, moving object distortions. If you look at the picture in the on the upper right there, that's not a melted propeller. It's actually a temporal aliasing of the spinning propeller with a rolling shutter CMOS image sensor. Below that, we have what's called the jello effect, which is a camera, in this case, mounted on the handlebars of a motorbike, and it's vibrating. And that's creating that wobbly effect there, classic, which has become commonly known as the jello effect. So you might say from this, why not just use global shutter? Well, global shutter pixels have to be larger. They also have substantially higher read noise than rolling shutter sensors. So if you can manage these kind of artifacts, rolling shutter is generally the best choice. At the pixel level, we have two dominant technologies, front-side illumination and back-side illumination. In front-side illumination sensors, FSI, we have the photodiode below the metal wiring. And this impacts sensitivity, light acceptance angle, optical crosstalk being photons that are captured by the wrong photodiode. In the newer technology, BSI, which has actually been around from the days when people would polish wafers by hand, but it's new in that it's become commercially available at viable price points. In this technology, the wafer is flipped and bonded to a blank wafer or an ASIC layer and then thinned down. And then the color filter array and microlenses are built on top of the thinned photodiode layer. There are a number of key sensor specifications that impact image quality that we need to pay attention to. First is full well capacity. It's really linear full well capacity. The response of the pixel may be greater than this, but then you start to move beyond the linear region. For small pixels, we might typically have a 5,000 electron linear full well capacity. For medium pixels, that might be in the 10,000 plus electrons. And then for large pixels, 50,000 electrons and greater. Sensitivity is typically quoted as a voltage swing per lux seconds, microvolts per lux second. Read noise, which I mentioned earlier, is the noise floor, RMS noise floor measured in electrons. And as a reference point there, for a small pixel sensor with low noise, would have a read noise around 2 electrons. Resolution is really a measure of linear resolving power, but colloquially, it's come to mean the number of pixels. And this really means in a optical imaging system, higher resolution means higher spatial sampling of the optical modulation transfer function, MTF, which I'll talk about more later. There are many, many image quality metrics. I'll just touch on a few here. First is signal to noise ratio, which is the ratio of the signal from photons to unwanted noise. Quite a useful metric that came from mobile phones is SNR10. And this is the number of lux being a measurement of luminous flux per unit area, in order to achieve a signal to noise ratio of 10. Dynamic range, that's the ratio between the maximum output signal level and the noise floor. And something to be aware of is sensor companies typically misrepresent this as the maximum output signal at the minimum analog gain divided by the noise floor at the maximum analog gain. And this is unachievable within a single frame. So do watch out for that. Dynamic range is a log scale, so it's 20 times the log of the brightest lux over the darkest lux. Resolution, as we mentioned, not really about pixels. It's really a measure of the smallest features that can be resolved. And we'll be talking about that in more details later in the talk. There are a number of different image sensor interfaces. There are a number under the MIPI standard. The DPHY, which was dominant in cell phones, has been dominant in cell phones for at least a decade. It allows up to 4 differential paired lanes with a separate clock lane. MIPI CPHY is a higher performance interface with embedded clock. This works using three wire lanes, which are called trios. And it started to gain traction in high performance phones. And while it's been around for a while as a standard, it looks like it's gaining broad adoption. It is likely to get more broadly adopted over time and start to move beyond mobile into other segments. We have a new standard called APHY, which is a MIPI standard for automotive adoption that adds some specific features. Automotive was starting to use DPHY. It really wasn't designed for that application, and so the MIPI committee has come up with this new APHY standard. Then we have various proprietary interfaces, LVDS, sub-LVDS, SLVS, and it's important to select a sensor that will directly interface with your processor, your system on a chip, or you have to accept the added cost and can be significant power of an external interface bridge chip. Typical commercial sensors have a dynamic range of around 70 dB. If you want to image beyond that dynamic range, which is often necessary if you're working in bright daylight, then you need to adopt high dynamic range technologies. And there's a multitude of techniques to extend the dynamic range that can be captured. The simplest is multi-frame HDR, where you capture sequential frames with a long and short exposure time. sometimes a mid-exposure time as well. And the long exposure captures the shadows. The short exposure captures the highlights. And then you can stitch the two together to create a single higher dynamic range frame with a higher bit depth. And for scenes with motion, this technique can result in significant motion artifacts, specifically ghosting. And you can see that in the image in the upper right, which shows someone at GoPro juggling. We don't all do this kind of thing all the time, but you can see their ghosting from their motion. That's, I will point out, an older generation of GoPro camera. We do much better than that today. Then you can use overlapping multi-frame exposure, where multiple exposures are produced on a line-by-line basis rather than frame-by-frame. What this does, it greatly reduces the motion artifacts by minimizing the time delta between the different exposure readouts. There are a number of different spatially interleaved methods where the multiple exposure times are captured simultaneously by varying the exposure time of different groups of pixels. So you can have alternate lines, zigzag patterns, etc. This almost eliminates HDR motion artifacts, but comes at the cost of reduced resolution and aliasing on high contrast edges. Continuing on with high dynamic range techniques, there are dual conversion gains. This is a technology that allows the pixel responsivity, microvolts per electron, to be switched between two values. This can be used in a multi-frame or spatially interleaved manner with similar characteristics to those I just described, but with improved noise, as you don't have a short exposure where you're effectively throwing away photons. There are logarithmic pixels. These are pixels where they either have a completely logarithmic response or a logarithmic response region that greatly extends the dynamic range compared to a linear mode pixel. The issues here are mismatches between the pixel response curves, and changes with temperature can create high fixed pattern noise and high photo response non-uniformity. A newer technology is overflow pixels. These are pixels that contain an overflow gate that can allow charge electrons to flow to a secondary storage node. The downside of this technology is it requires an additional storage node per pixel and an additional control line. And so this means that this technology only works today for larger pixels around 6 microns or larger. Now, let's talk about the optics for image sensors. When matching optics with an image sensor, we have to take care of a lot of different parameters, and I'll go through those in the following section of the talk. Optical format is probably not what you think. So a 1/2.3 inch format sensor does not have a diagonal that's 1/2.3 inches, 11.04 millimeters. It's actually about 1/3.2 inches, 7.83 millimeters. This is because we have an old convention that's a legacy of imaging tube technologies, where the stated optical format was the mechanical diameter of the tube. And in the bottom right there, you can see a 2/3 inch format Vidicon tube. So optical format is about 1.5 times the sensor diagonal. Then we have a different format. So for film cameras, 35 millimeter format is actually 36 millimeters by 24 millimeters, 43 millimeter diagonal. And the convention here is actually the spacing between the film feed sprocket holes. So 35 millimeter is the distance between the holes in film. Now you can pair a lens with a sensor that's a smaller optical format. That's okay. It will crop the field of view, and it might also create a chief ray angle mismatch issue, which we'll talk about in the next slides. Chief ray angle is the angle of light rays that pass through the center of the exit pupil of the lens relative to the optical axis. So you can see in the diagram with the tree, you've got some light coming from the top of the tree, passing through the center of the aperture, and then landing on the image sensor. Often you'll see CRA is quoted as a single number, which will be the maximum CRA, but it's actually a curve. And in fact, in mobile lenses, it reaches a peak at about 80% image height and then drops back down. So it's non-monotonic. And the image sensor will typically offset the position of the micro lenses to compensate for the anticipated change in CRA across the ray produced by the lens. and that stops or minimizes the drop-off in sensitivity. So you want to have a good match between the lens and the sensor CRAs, otherwise you will increase the luma and chroma shading. Good rules of thumb are for pixels around the 1 micron size. You want to have a CRA match between the lens and the sensor within 2 degrees. For larger pixels of, let's say, 2 microns, then that can be opened up to about 5 degrees. So focal length is a measure of how strongly an optical system converges, or it could be diverges, light. Generally, we can use the thin lens approximation, where 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Calculation for magnification is straightforward, minus the image distance divided by the object distance, which is equal to the image height on the sensor divided by the object height. Field of view, FOV, is determined by both the focal length and the distortion of the lens. For a rectilinear lens, which is one where straight features in the scene form straight lines on the sensor, the field of view alpha is 2 times the arctan of the sensor size divided by twice the focal length. And that's true so long as the object distance is much greater than the lens focal length. For lenses with non-rectilinear distortion, like GoPro lenses, the calculation gets more complex. For vision systems, we're generally going to be dealing with rectilinear lenses. Field of view is quoted as the diagonal field of view, DFOV, horizontal FOV, HFOV, and very rarely vertical FOV. And sometimes it's quoted without defining which is being used. So generally, it's best to ask. F number is the ratio of the focal length to the diameter of the entrance pupil. The entrance pupil is the image of the physical aperture when seen from the front, the object side of a lens. And N, the focal length, is equal to the F number is equal to the focal length divided by the diameter of the pupil. For the smaller n, the more light reaches the sensor. A lens with a smaller f number is often referred to as a faster lens because it permits a faster shutter speed. We use a stop scale for f number, with each stop being half the amount of light passing through the optical system. So for example here, an f1.4 lens lets in twice as much light as an f2 lens, which lets in twice as much light as an f2.8 lens. There's a relationship between f number and the resolution limit of an optical system. So diffraction of light by the aperture creates a lower diffraction limit to the resolution of a camera. And this is another quantum mechanical effect. A circular aperture creates an airy disk pattern on the image sensor, as can be seen in the upper right picture there. And the smaller the aperture, the larger the airy disk. For small pixels or lenses with high f numbers, then real-world performance can be limited by this diffraction limit. The diameter of the airy disk, the first null, the first dark ring, D, is 2.44 times the wavelength times the f number. And the table on the right shows a good guide to minimum resolvable pixel size versus f number. This is for detecting edges. If you're imaging points like stars, then the limits would actually be higher. So for an example, an f2 lens could resolve 1.1 micron pixels quite reasonably comfortably. An f2.8 lens would be able to resolve 1.5 micron pixels. Depth of field, DOF, is the distance between the farthest and nearest objects that are acceptably in focus. And it equals twice times the object distance squared multiplied by the f number multiplied by the circle of confusion, which is the acceptable blur circle, divided by the square of the focal length. So depth of field increases with the focus distance squared, the circle of confusion, which could correspond to larger pixels, and the f number, although a higher f number comes at the cost of reducing the amount of light reaching the sensor and also can start to have limits because of diffraction. Depth of field decreases with the focal length squared. So a shorter focal length lens has a larger depth of field. So either a wider field of view or a smaller sensor will increase the depth of field. A lens is designed for a specific wavelength range. The wider the wavelength range, the more difficult the design becomes, leading to a higher cost-performance ratio. A lens designed for visible light will have poor performance in the near IR and vice versa. So a lens should be selected to match the application. So if you are building a camera for near IR only, you should use a near IR lens. If using visible and near IR, a lens designed for the full wavelength range should be selected. Modulation transfer function, or MTF, is a measurement of the sharpness and contrast of a lens over a range of spatial frequencies starting at 0. MTF plots allow us to evaluate a lens for a particular application and for lenses to be compared. An MTF score of 30% means that an edge will be well resolved. The horizontal axis in this type of MTF plot is line pairs per millimeter. Higher line pairs per millimeter correspond to smaller features. And the highest spatial frequency that can be sampled by the image sensor is 1000 divided by 2 times the pixel size. This type of MTF plot typically contains lines for various image heights. For example, 0%, which corresponds to the center of the image, 60%, which are the middle regions of the image, and 90%, which are the corners of the image. Plots will typically show different lines for sagittal and tangential directions. Sagittal lines run parallel to a radius, tangential lines are perpendicular. If you see a single number, it's likely that what you're seeing is the average of sagittal and tangential. Alternative plots will show MTF versus image height plotted for specific spatial frequencies. Now, a warning on MTF, unless otherwise stated, the quoted MTF for a lens is for the as-designed lens, the perfect lens without any manufacturing tolerances. Actual as-built MTF will always be worse than this. This can be simulated using Monte Carlo simulations and can be measured on optical test equipment. Relative illumination is a measure of the light roll-off intensity from the center to the edge of the image circle. It's often stated as a single number, which is the relative illumination at 100% image height. But again, it's a curve. The plot on the right is for a lens with an 88% relative illumination, which is very good. A typical mobile lens, by contrast, will have a relative illumination of 30% or lower. And this shading effect means that the corners will be noisier, will have lower SNR than the center of the image. The sensor will also have some roll-off in sensitivity with CRA. So the camera relative illumination is really the product of the lens relative illumination and the sensor roll-off. Relative illumination can be corrected by applying a spatially varying normalization function, but this has the effect of amplifying the noise in the corners. Stray light is light that's scattered within an optical system and reduces contrast. Ghosts are typically the term ghost is typically used to refer to spatially localized reflections that can obscure details or confuse machine vision. Sources include imperfect anti-reflective coatings. Typical coatings on a glass lens element reflect about 0.3% of normal incident light. Typical coatings on plastic elements reflect about 0.4% of normal incident light. The edges of lens elements can be sources of stray light. Sometimes putting an ink around the edge can help, not always. Mechanical surfaces, which can then be blackened or textured to help. Diffraction of the image sensor. This can actually bounce back up, hit optical surfaces and bounce back down into the image sensor. And then dirt and oils on optical surfaces can be a source of stray light. These can be simulated if you have the full lens design using specialist tools such as Fred, Light Tools, and ASAP. It can also be measured in the lab using a point light source, typically a fiber bundle, and a robotic stage to rotate the camera. The picture on the right is fake stray light rendered in Photoshop. It's subjectively good for art, but not good for machine vision. Vignetting is the unintended blocking of light rays towards the edge of the image. So check for mechanical features for possible sources of blocking, filter windows and holders, and main product housing. If you can have an optical engineer generate what's called a mechanical field of view to import into your CAD, that's a good way of checking for interferences. And in doing so, it's important to include mechanical tolerances to determine any clear window size, sizing. So the lens to sensor centration, the lens to sensor tip tilt, and then the camera module to housing alignment tolerances in X, Y, Z, and tip tilt. There are a number of other design factors that we have to pay attention to, so I'll go into a couple of those in the next slides. First one is thermal considerations are extremely important with CMOS image sensors. Dark current doubles about every 6 degrees C, and as dark current increases, dark signal non-uniformity will also increase. Dark signal shot noise, which is the square root of the number of dark signal electrons, can start to become a factor at higher temperatures. Hot pixels, which we discussed earlier, they increase with temperature. As temperature increases, defects become thermally activated, and so you'll start to see more of those hot pixels. The overall sensor black level, the corrections for that can get worse with temperature, so you can start to see the black level drift around the ideal. So the thermal design of a camera should be considered up front. It's important to design a low thermal resistance path from the sensor die to the ambient environment. And a couple of relatively simple techniques are shown here. On the left, we have thermal vias running through a printed circuit board. These are just plated through holes, which are actually quite effective in carrying heat from the image sensor down to the backside of the printed circuit board, where a heat sink can be attached, or the chassis of the camera, using a thermal pad. Another technique sometimes used is to have a hole in the printed circuit board and have a cold finger of a heat sink running through to make contact with the back of the image sensor, again using a thermal pad. Image sensors are mixed signal devices, and it's very important to pay attention to power supply noise, particularly on analog supply rails. A good design approach is to have a dedicated LDO for the sensor analog supplies. And then it's important to pay attention to placement of decoupling capacitors. They want to be close to the image sensor with low impedance routing. You can ask your sensor supplier for a module design reference guide, which may have some layout guidelines, but make sure that you prioritize the placement of the analog rail decoupling capacitors to put them as close to the image sensor as possible with the minimum number of vias. And then once you have your first operating camera modules, you should capture images in the dark with no image processing and extract the different noise components. And the analog supply is particularly prone to creating temporal row noise. So if you look at the temporal row noise in your captured images, and if it's worse than the manufacturer's evaluation system or some other reference design, the chances are that you need to improve the noise on the analog supply with filtering or changes to layout. So how do you select a sensor and lens? This is actually quite complex, but in the next section, I'll give you some rules, some steps to go through to facilitate this process. So when selecting an image sensor, start off by determining the key requirements, determining resolution requirements. What is the object space resolution? What is the field of view required? So how much of the scene do you need to be able to see in a single frame? What is the maximum object distance? And what are the minimum number of linear pixels that are required for feature recognition? And then from that, you can determine the pixel size, object space resolution multiplied by the field of view divided by the sensor size. Determine the wavelength of light that's going to be imaged. Is it, for example, visible or near IR? Do you need to select a near IR enhanced sensor? Color, do you need color, which may be full RGB, mono plus red, etc., or is a monochrome sensor required for the system? Dynamic range requirements. Are you going to need high dynamic range, or are you going to be operating indoors where generally normal commercial image sensors will have sufficient dynamic range? Will you have high speed motion of either the camera or the scene? And that can then be a factor in determining whether to use rolling or global shutter. And then, as we talked about earlier, interface requirements for your SoC should be one of the factors in selecting the sensor. So user requirements from the previous slide to select a sensor evaluation kit, EVK. Look for sensors intended for similar applications. And many of the sensor companies have online product selection tools or can support at the sales or application engineering level. Once you purchase an evaluation kit, if possible, pair it with a lens that's a close fit for your final application. We'll talk about that in the next section. And then test the evaluation kit in your application with minimum illumination conditions. If the lens field of view doesn't match, then you can adjust the object distance or your chart size to compensate. If you find that the low light signal to noise ratio is acceptable, then you can proceed on to the lens selection. If the low light signal to noise ratio is not acceptable, then can you achieve your required SNR by adjusting the lens aperture? So if you go to a larger aperture, lower F number, the trade-off there to pay attention to is depth of field, and a lower F number lens will generally have larger, it will be larger in size and have a higher cost. Can you achieve the required SNR by holding the F number constant, but increasing the exposure time? The trade-off there may be motion blur. So if the signal to noise ratio requirements cannot be achieved, then select a larger sensor, which allows for more light collection, and repeat this process. Trade-offs to pay attention to there are depth of field, sensor cost, and lens size and cost. Evaluate dynamic range. This is actually one of the more difficult tests to perform. I won't go into details here. There are online resources like Imatest test software tutorials that can help in conducting this test. Now we'll move on to selecting a lens. So first determine the optical format dictated by the sensor size. Select the field of view, which will dictate the focal length. Determine the target F number. Check your depth of field. And then take a deep look at MTF. From a resolution study, determine line pairs per millimeter resolution needed. Remembering that a MTF of equal or greater than 30% at the target line pairs per millimeter is a good rule of thumb for being able to detect edges. And then check the MTF across the field, center, mid, and corner regions. Pick a lens with a CRA that closely matches the sensor CRA specification, and check for the impact of relative illumination on the performance in corners, where SNR will decrease. Determine if the lens includes an IR cut filter or IR passband or whatever other filters needed, if your system requires one, of course. And then check if the lens is suitable for your dynamic range requirements. If you're imaging in a high dynamic range scene, then that requires very good anti-reflective coatings. I'll finish off with a number of resources. There are many aspects to building an imaging system, but hopefully in this presentation, I've given you some pointers and some steps to take in designing your system.